apart.
Yeah, let me just say this about this problem. This is problem 2-4 in Dr. Wentworth's book. You have two wires and they're separated by a distance d, and they have a given radius a. And then there's an epsilon relative between them of what? Do they say it's air?
Yeah, air.
Right, so it's epsilon relative of 1. Now, the thing about this is they assume you understand capacitance, which we haven't covered yet. But in physics, you had the concepts of capacitance. Now, I wouldn't expect you to know capacitance for these types of things unless it was covered in this course. So there's a formula in his book that he gives you for capacitance of two wires. Did you see that in the reading?
Yes. It's pi epsilon
That's
over.
right. Over natural log. Really, it's, in this case, it would be d, approximately d, pardon me, over a. He has about that, doesn't he?
He has inverse hyperbolic cosine of d over
It's still in the Koch formula? All right. So, and is it d over a? D over the
d
rate?
over 2a
2a?
and inverse.
What?
Inverse Koch.
Koch minus 1?
Yeah.
All right. Well, I mean, how many have had hyperbolic functions? Koch, and you have, yeah. Your calculator should have a function to do that. Just so you know, if you have a Koch, anything, I'll use theta, that's e to the theta plus e to the minus theta over 2. The sinh of theta is equal to e to the theta minus e to the minus theta over 2. And then the tan h of theta is equal to e to the theta minus e to the minus theta over e to the theta plus e to the minus theta. These are very similar to the formulas you get for the hyperbolic formulas for, the Euler's identity for sine, cosine, and tangent. Remember, for cosine, it's just what? It's e to the j theta plus e to the minus j theta, right, over 2. Here, you get rid of the j. The h signifies it's hyperbolic. That's the bottom line. For sine, when it was just the regular one, it was e to the j theta minus e to the minus j theta over 2. Do y'all remember these? This is basic Euler's identity. And here, for tangent, it's e to the theta minus e to the theta over e to the theta plus e to the minus j theta. And this is really, what this is sinh of theta over Koch of theta. Now, that's just, it's in the back of his book, he has these. I want to say this: for two wires separated by a given distance e, where the wires have radius a, and you want the per unit meter capacitance, there are other formulas. This is one that he has in his book. We'll cover that later in chapter 3 in electrostatics. But the real thing about this is he's looking for that problem. Is it characteristic impedance?
He's looking. Well, you had us looking for all of the per unit terms.
And I'm going to show you a trick here. This is a little further down, but this is a nice trick. Whenever you have a transmission line, do you all agree it's a transmission line? The cross section doesn't vary versus distance. Then there's two conductors separated by a dielectric. Do you all agree with this? So this is a true transmission line. You can use this formula, write it down. I don't know if he has it in his book. You can take the capacitance per unit length times the inductance per unit length, and that's equal to the epsilon relative. Really, it's equal to epsilon times mu if the region is homogeneous. Now, what I'm going to say is, if these two wires are in a region where neither mu nor epsilon changes, that will work. It also means this: if this was something where I had, say, half of this region had epsilon 1, and the other had to have epsilon 2, you couldn't use that formula. All right, this is something, if everything is the same, all the media parameters are the same. We didn't cover this, but in physics you dabbled with it. You remember permittivity in physics? You remember permeability, the symbols permeability in physics? So that's what these are, and they're material constants. But that means I can automatically get the inductance per unit length is just epsilon mu over CL. Follow me? We've got C, we can get that. Now, the characteristic impedance, we can get by simply saying Z naught. I covered characteristic impedance last time, right?
Mm-hmm.
Characteristic impedance is nothing more than what? The square root of, normally it would be what? It would be R plus J omega L, these are all per unit length of parameters, over G prime plus J omega C prime. Do you all remember that formula? Now, because there is no resistance and no conductance mentioned, you assume they're both zero. And that means R and G go away, the J omegas cancel, and I get simply the square root of L prime over C prime here as the characteristic impedance. He asked for characteristic impedance, right? Isn't that the problem?
I don't. I forget about that.
I don't have my. Can you?
I don't have it for
You have a book. Can you read me problem 4, what they asked for? By the way, you don't have to hold that. You can probably sit it down.
My phone's kind of small, so they can't.
What's that?
They can't arc up like that.
Oh,
So
you're getting it, right? All right. Did you guys send me a link, by the way?
I had just uploaded it. I didn't. You wanted it on the OneNote?
No, I mean, just send it to me and I'll send the link to everybody.
Okay.
Can you do that?
Mm-hmm.
All right. And you too.
Okay.
All right, now, go ahead.
Which one is it? Because like in the back, in the problem section, 2.4 is like a MATLAB. It says
It was
the
2.2.
2.2.
Yeah.
Calculate the distributed parameters of 1 millihertz for twin link cables consisting of
What?
26 copper conductors with center separated in air about 1 centimeter.
Wait, say that first part again.
Calculate the distributed parameters
Go ahead.
at 1 millihertz for twin link.
Millihertz?
What is it?
Megahertz.
Megahertz, okay. All right, so we got F equals 10 to the 6. A millihertz is something, that's geofrequencies when you do these things that have to do with the resonances of the Earth's cavities. Go ahead.
For twin lead cables consisting of AWG 26 copper conductors with centers separated in air about 1 centimeter.
And you got the radius for that, Josh?
Yes, it was.
I'm assuming. And what do they want now, specifically?
It just says calculate the distributed parameters.
All right, well, I'm going to tell you right now, for this one, for copper cable, did he give you, he gave you a table with AWG?
There were a bunch of tables in the back of the book, and I couldn't figure out which one was which.
All right, I'm going to tell you this. Some of this problem is going a little beyond where we should go. I thought he was just going to do the characteristic impedance of this one. But in the answers, does he have an R, G, L, and C? All right, that means what he had to do is get the conductivity per unit meter, and he had to get, well, really just conductivity per unit meter, but I'm gonna say this. This will be the capacitance per unit meter. We need that, right? This will be the inductance per unit meter. Now, the resistance per unit meter is something I'm gonna put down for you, but does he want, problem is, this problem probably relates to skin depth, and this is further down the line. We don't have we haven't gone through the physics of how to do that part. For now, I'm just going to say for this problem, get this part and this part. Did this answer come out right?
I gave up when I was trying to get the per unit resistance.
No, forget that. Did you try this one or no?
No,
Did anybody try this, Roger? Let's do it right now. You have an answer, right?
no.
There's no answer for that one?
It's on your OneNote.
Wasn't there an answer for this one in the back?
Just got the book. I was
Oh, all right.
open it before right now.
There should be an appendix in the back.
You see the index. Oh, there it is.
Frequency, the only thing this frequency would have to do with is a skin depth, and that's something we definitely don't need to worry about. These are the two things you want to calculate. This and this.
Okay.
And this is just a straight plug and shove. Y'all follow me on this sewing class? If you have a formula, by the way, this is more like a technician's thing right now than an engineer's thing. Engineer works from first principles. Here, we haven't touched capacitance yet. What I really want you to do is simply calculate based on a formula this, and then get this from it, inductance. Remember that? And then the characteristic impedance is just 1 over that. And for all intents and purposes, whenever you have wire line like that, usually the loss per meter is very, very small. So the amount of attenuation is trivial for any applications that are, say, within maybe 100 feet. But beyond that, then you have to take loss of effect. All right.
They don't have an answer for that one.
Tell you what, we're gonna table that, we'll come back to it. Did I say I was gonna work that in class, by the way? Well, which one? I said I was gonna work one in class.
I think that was number 2.
This one?
No.
Oh, the second problem,
Yes.
posted. All right. Can you tell me what that is?
If I can pull up the one note.
I got my computer here, I should be good.
I've got the problem word. I don't know which one it is.
Let me take a look.
I don't know which number.
Yeah, this is an infinitely long transmission line. So this is the second problem that's on OneNote. And what it has is an infinitely long transmission line. Oh, well, no, 100, is it a 100-meter long transmission line?
Infinitely long.
And they have, you're right, infinitely long transmission line. And they have a frequency here of 100 megahertz, right? And then they give you R prime, G prime, C prime, and L prime. Is that right?
Yes.
All right, and they want, what do they want?
Z naught and the propagation constant.
All right, well, here is Z naught in a nutshell, right? So it's given. We have the RG, you might as well just tell me what they are. R is what?
R is 1 milliohm per meter.
That's 10 to the minus third. Go ahead, G.
G is on a different line, 0.
Okay. C,
2 picofarads per meter.
2 times 10 to the minus 12. Go ahead, and L.
1 times 10 to the minus 6.
All right, so they're always per unit meter parameters. So we have a frequency of 100 megahertz just for the sake of consistency. Z naught would be the square root of R prime, which is 10 to the minus third, plus J omega is 2 pi times F is 10 to the 8th, times L, which is 10 to the minus 6, over J omega C, which is J times 2 pi times 10 to the 8th, and C on this one is 2 times 10 to the minus 12. So if you get your calculator, you can see what that is. That's Z naught. And the gamma, the propagation constant, is the square root of R prime plus J omega L prime times G prime plus J omega C prime. So you can take a look at that and literally just plug those values in. R prime is 10 to the minus third plus J times 2 pi times 10 to the 8th, and then it's times 10 to the minus 6. It's multiplied by J times 2 pi times 10 to the 8th, and then it's times C prime, which is 2 times 10 to the 12th. And you can give me that too. So what did you get for Z naught?
707 minus 5.6 times 10 to the negative 4.
707 what?
707.107 minus I,
707.107?
yeah, minus I or J 5.6 times 10 to the negative 4.
Just for the basis of reason, this is about 0. All right, so you can say it's about 707. About 707 ohms right there for characteristic impedance. For gamma, what did you get for gamma? Propagation constant. Did you get that?
I got 0.707 times 10 to the 9.
All right. Well, let's just take a look at that then. When I look at this, I have 10 to the minus 6 times 10 to the 8th. That's 10 to the second. And times 2 pi times 10 to the second is much greater than 10 to the minus third, so forget that for now. So then when I look at this is basically just the square root of L over C. So just tell me this, what is the square root of L? 10 to the minus 6 over C, which is 2 times 10 to the minus 12. That's equal to it's equal to the square root of 1. 1 over 2 times 10 to the minus 6, which is really 10 to the 6, so just tell me what the square root of 1/2 times 10 to the 6 is. It's going to be 10 to the third, less than 10 to the third. It's going to be about 700. Is that what it is? 707? That should be the right answer. The resistance value here is trivial. And that is about 707 if you do that. Right? Okay. What'd you get for the propagation constant? It should be basically imaginary.
Yeah, has a very small real component.
What is the value though?
707 or 7.07 times 10 to the negative 7.
Yeah, that's right.
And then
Plus J.
plus J 0.888.
0.888. Now that's radians per meter, and this is Napier's per meter. Yeah, that's right. Okay. The one problem I asked you to take a shot at was the 10, right? 2.10, 2.10. You see that in the notes on OneNote? I think it's there, isn't it, guys? No? What's on my OneNote? Yes, it was. Try problem 210, and I give you the answer. Do y'all see that or not?
Yeah, I missed it.
All right, the reason I wanted you to do it is because it leads into the next topic, which is attenuation in dB per meter, and this is important. Decibels are used all the time. How many have heard of decibels? Has it been explained to you? In what course?
Analog.
Analog electronics? Okay. Has everybody had analog? Anybody not have analog? You didn't have? Not everybody's had analog. Did you get any laboratory stuff? Josh, where did you hear it?
We talked about it some in linear last fall and also in Digitron.
I figured you'd get it in digital electronics. I do it in analog. I do it in signals and systems, but some professors, you don't have to cover that topic, so sometimes some people miss it. I want to go through decibels. It's real important. In engineering, many times we deal with things that are 10 or 12 orders of magnitude in difference. And it's insane to talk about the ratios when they have 10 to the minus, say, 10th in terms of the scale, or really 10 to the 10th scale. So we do it with decibels. Decibels is taking the log, really, of the number. So first, what is a dB? This is a decibel. It's named after a guy. And what a decibel is depends on if you're talking about voltage or current or power. So a dB in general is 20 times the log of a voltage. Or a dB is 20 times the log of a value of current in amps. That's generally true. When you deal with power, this is voltage, this is current, this is in amps. And this would be power in watts. So in power, a decibel is 10 times the log of the actual power term. This is the general terminology used. Now, specifically when we talk about decibels, there are some units of measurement that are common. One is dBm, and that's for power, it's the most common. So if we talk about power and we talk about dBm, m indicates 10 to the minus third, and what it is a reference. So if you have, this is called, dBm is really decibels with using a milliwatt as the reference. And this is a ratio, it's 10 times the log of the actual value of the power you're talking about, divided by 10 to the minus third. If we talk, the other couple of common references are dB microamps, and that's 20 times the log of the value of the current over 10 to the minus 6, and dB microvolts, and that's 20 times the log of the voltage over 10 to the minus 6. So you can really see the trick here is when we're talking about, these are all units. When we talk about dB microvolts, it's micro indicates 10 to the minus 6, that's the reference. Since it's a voltage, you have a 20 in front of this. These are all log base 10, by the way. If we're talking about dB microamps, it's 20 times the log of I over 10 to the minus 6. Again, the micro indicates that's the scale factor. If it's dBm for power, it's 10, because it's power, times log of the power over 10 to the minus third. The m indicates the scale factor. Follow me on this, guys? Now, these are units. There's another thing that's commonly done, and it's talking about how many dB of loss occurs. How many have heard that kind of terminology? You know, when you get cable, like coaxial cable, it's rated as like 4.5 dB per 100 feet at a certain frequency. As the frequency goes up, or basically doubles, it'll be rated at 9 dB per 100 meters, all right? And what they do with cable, most cable, is give loss in either per 100 meters or per kilometer. That's normally the way it's done with any kind of long cable that you're gonna have strung a long way. Coax is the best example of that. And, Charter's internet, you'll have, it's Spectrum now, but the cabling they have there is 75 ohm, and I want to say it's 4.5 dB per 100 meters at 100 megahertz, and I'm not sure what the actual operating bandwidth is for Spectrum. I don't know the entire band, but that's probably gives you an idea. So now let's take a look at dB actually being used for a problem in terms of a ratioing. So here we're going to have a system, and I'm going to put P in here, whatever it is, and I'm going to say it's going to have a loss of 60 dB, and I want to know what comes out. Are you with me? So the way you always do a problem like this, 60 dB losses means you're going to subtract 60 from the dB coming in. And it doesn't matter the units. This could be power and dB, I mean, it does matter the units. It has to be in decibels, but it could be dB milliwatts or just dB watts. But I'm gonna do in dBm. So, and we're gonna do this, we're starting with a very common thing. Suppose I put in a power input as 1 watt. And everybody appreciates 1 watt is a simple number, right? So what is 1 watt in terms of dBm? All right, so I'm going to put power now in terms of dBm. This is power in terms of dBm. That would be 10 times the log of 10 over 10 to the minus third, right? All right, I put the, 1. I put the input power, which is 1, and I divide it by the scale factor, or really the measure, the standard, 10 to the minus third. Take the log of it and multiply by 10. Well, this is really what? This is the log of 10 to the third, isn't it? 1 over 10 to the minus third. And the log of 10 to the third is just 3, isn't it? So 3 times 10 would be 30 dBm. That would be the power dBm that would be input. Now what's coming out? I got 30 dBm going in, I subtract 60 dB. One of the common questions people say, but it doesn't have an M on the end. 60 dB of loss is 60 dB, you just take whatever value of this is and subtract 60 from it. It's gonna be down by a factor of 60 or subtract this. If it was just dB, it would still be down by 60. Everybody understand that? So the output power here in dB, right here, P out, would be equal to 30 minus 60 dBm, or it would be minus 30 dBm. Now, translate that into how much power in watts. Do the inverse problem, all right? How much power in watts? If I got an output of minus 30 dBm, what does that mean? That means I have 10 times the log of whatever the output power is, right? Over 10 to the minus third. You all see what I'm up to here? Now I set it equal to the formula, right? And what happens? Well, when I have this, I'll take the minus 30 divided by 10 first, right? I have minus 3. And that's equal to the log of P output divided by 10 to the minus third. How do I get rid of the log, people? Take both sides, raise it 10 to that power, correct? So that means now I have 10 to the minus 3, right? Equal to P out divided by 10 to the minus 3. Or really, what is my P out? Multiply both sides by 10 to the minus 3. What do we get?
10 to the minus 6.
That's right, 10 to the minus 6 watts. And one thing you can almost pick up on right now, whenever I have, no matter how many dB, here it's 60. 60 dB means, is it 6 orders of magnitude less? Well, if I got 1 watt going in, 6 orders of magnitude less is going to be 10 to the minus 6, correct? If it was 30 dB of loss, I would have 10 to the minus third coming out. If I have 100 dB of loss, I would have 10 to the minus 10th coming out. Follow me on this, class? All right, so that's dB in a nutshell. The interesting thing is, well, I'll just leave it at that for now. I wanted to do that. Now, if you look at problem 610 in your book, how many saw 610 in the homework? Nobody? I'm just gonna caution you, make sure you do this homework, because God help you if you don't. This class, if you've had me before in signals and systems, I think you can appreciate things pile up quickly and you can really get lost. In this course, you can get buried quick because we're gonna go through 3 disjoint things. We're gonna go through transmission line theory, then electrostatics, and then magnetostatics. And there is not a natural coupling between them. So you've got to stay on top of this stuff because it can really just blow you away. You have the book, right? Problem, does anybody else have a book here?
Okay.
All right, so give me problem 10. It's 210. Because this should be an easy one for us based on what I just said.
If 1 watt of power is inserted into a coaxial cable and 1 microwatt of power is measured 100 meters down the line, what is the line's attenuation?
Attenuation. 100 meters, right?
Yes, sir.
So this is P out. Now, think about this problem with respect to what I just said. I got 1 watt in, I got 10 to the minus 6 watts out. How many dB of attenuation? 60 dB, right? There's a difference of 6 orders of magnitude, it's 60 dB. Follow me on this, everyone? An order of magnitude is a factor of 10. From 1 to 10 is 1 order of magnitude. 1 to 100, 2, 1 to 1,000, 3, or from 1 to 10 to the minus 1 is 1 order of magnitude less. This is 6 orders of magnitude of attenuation. All right, that means 60 dB. So we have, in terms of dB, we have 60 dB of loss, right? And you can put down loss just to make sure. Over what distance? This is how simple this problem is. Over what distance? 100 meters. And that is alpha, or 0.6. That's how easy it is. Are you with me? Did you have a question?
What's L equal to?
100 meters, it's the length of the line.
Okay.
Sorry if it's a little messy. Now, I might have a mark. Okay. Okay, now I actually got to relate to two things. I hope everybody appreciates dB, and I'm going to give you a relationship between the alpha that's in Napier's per meter and the alpha that's in dB per meter. And this can be a little confusing, so I want you to please pay attention to this. Now, when you get cable, if you buy anything commercially, if you get a job and you're working as an engineer, and they tell you to go get some cable that has a loss of less than, say, 30 dB per 1,000 meters or something, one of the things you always have to be attuned to is the frequency of operation, because loss is a strong function of frequency. Usually it doubles. If you have, if you double the frequency, you basically double the loss in dB. For instance, if you have 4.5 dB per 100 meters of loss in a cable at 100 megahertz, when you go to 200 megahertz, it usually doubles. It would be about 9 dB of loss per 100 meters. Just keep that in mind. It's always the frequency of operation becomes critical. Something else, now I'm going to relate this to what we left off last time. Do y'all remember when I did the power formula, I said the average power flowing in a transmission line was equal to 1/2 the real part of really the voltage in the transmission line times the current conjugated in the transmission line. Do y'all remember that from last time? You have excellent handwriting. Do you remember that, right? Now, once I put in the equations for this, I said if we're just looking at power traveling in the plus Z direction, we found out that the average power that's flowing down the transmission line was actually 1/2 the magnitude of V naught squared. Now that's the voltage at the beginning of the transmission line. It's the applied voltage. And it's the magnitude, by the way. And it's divided by magnitude of Z0 plus. Now remember, Z0 can have an imaginary part, but it's magnitude. Then it's times the cosine of the phase angle of Z naught. Then it's times e to the minus 2 alpha z. Their alpha is in Napier's per meter. So remember, alpha is in Napier's per meter here in that equation. Yes?
What is Napier's meter?
Well, it's a unitless quantity. Remember, when you have the propagation constant, normally you have alpha plus j beta. Here, alpha is in Napier's per meter, plus j, beta is in radians per meter. But the reason I say it's unitless is because it's not really unitless, it's 1/meters is the units. Napier itself is one of these things we add on there. The reason I'm saying this is when we have an e to the, alpha, or e to the gamma z, this has to be unitless. E to that has to be a unitless quantity. So whenever you take gamma times z, z is in meters, gamma will have units of 1/meters. They call Napier to indicate it's just going to be an attenuation, and radian for the other one to say it's really a phase constant. That's what it is. Anyway, that's where alpha is here. There's a factor of 2 there too. Now, just look at this for 1 second. You all see how this term here is not a function of position? It's a constant, right? At a given frequency. So what we usually do is say the average power as a function of z is just some P0. And that P0 would be the power entering. Power entering transmission line. And then it's times e to the minus 2 alpha z. That would be in watts. So that's how much power is still flowing down the line versus z. And you can see as for any finite value of alpha, the further down the line you go, the less power is available that keeps flowing. You all see that, class? Now, what if we put this power in dBm, for instance, okay? Matter of fact, we'll just put it in terms of dB for now. Power in watts dB, or dB watts. So if I take that and I say, now I want the average power in dB, just dB, that would be 10 times the log of that power, which is P naught, times e to the minus 2 alpha z. I'm not even putting 10 to the minus 3rd there. I'm just gonna have dB watts, so that the actual standard is not a milliwatt, but a watt. What's that gonna be? Well, that's 10 times the log of P0, right? And then it's gonna be minus 20 alpha z times the log of e to the 1. Now, you know, when you have log of a times b, that's log of a plus log of b. Do you all agree with that, class? Log a, b. So what I did is take log of P0, multiplied by 10, broke it off, and then I took log of e to the minus 2 alpha z. Well, log of e to the anything brings the anything out in front, right? And it's just the log of e. Well, this is also 10 times the log of P0 minus, well, 20 times the log of E is 8.686 alpha Z y'all see that? If you take 20, does anybody have a calculator? Do this for me. Just take the log base 10 of E to the first power, or just E, and then multiply it by 20.
$1.00657 times 20.
Times 20.
Point 12 in nano.
I think something's wrong here. If you take the log of E times 20. Anybody else have a calculator? E, you have to put E to the 1.
8.685.
That's right. It's actually 8.686. It's 59 something. It's about 8.686 times alpha Z. Now remember, that's the power, average power, flowing in dB. Well, how much loss occurs per meter? As a matter of fact, we can do it this way. If I say this, if I go 1 meter down the line, first P, let me do it this way, P average in dB at Z equals 0 would be 10 times the log of P0. Do you all see that? If Z is 0, that term goes away, right? Now 1 meter down the line, P average in dB at Z equals 1 meter would be 10 times the log of P0 minus 8.686 times alpha. You all see that, class? The Z is 1, right? Are you with me, everyone? Well, the difference between here to here would be the loss in dB per meter. Do you agree? And what is the difference when we subtract them? Well, when we subtract that, we end up getting a total of 8.686 alpha equals the loss in dB per meter. Alpha dB per meter. And this is important. If you want alpha in terms of the decibel loss per meter, you take 8.686 times alpha in here, that's in Napier's per meter. So this is what's called the relationship or translation of one to the other. If you're doing things, suppose you have alpha in Napier's per meter, and they want to know how many dB per meter it is. You simply multiply it by 8.686, all right? I'm trying to make it as easy as possible, just understand this. Now, why would you want that? Because you might calculate alpha from one equational set And that value of alpha, like when we calculate alpha and we use this, the propagation constant, and we say it's the square root of all that stuff, R plus J omega L and G plus J omega C, and we end up getting alpha plus J beta, right? That alpha is in Napier's per meter. Got me on that one? So if you wanted to figure out in dB per meter, you would take that and multiply by 8.686, and then you would have the loss in dB per meter, and you could easily find the total loss in a 100-meter cable. Just multiply the length by the attenuation in dB per meter. All right? I'm trying to show you things that are useful for, in practical senses, for solving problems. All right, next. Okay, next, we're going to go into terminated transmission lines. I'm going to say this, that there's no transmission lines you really do problems with that don't have some termination. It just means, where do they lead to? A cable, I mean, it could be a TV, a modem, could be anything. Okay. Next. So this is going to be terminated transmission lines. You know, if you can, bring your books to class. Does everybody have a book now or not? How many do? Raise your hands. Okay. If you don't, please get one, because and bring them to class. In the next couple of lectures, I can reference things in the book very easily, and you can make notes in the book. You won't lose your book. You may lose your notes, though. Well, I hope you don't lose your notes. So when we talk about a terminated transmission lines are usually indicated by just drawings where you have two pieces of pseudo wire in the little sketch, separated by some distance. Then what they usually do is put a set, they have to have a measurement system. So usually they'll put this as the distance Z, at least Dr. Wentworth does, and he'll attach a load here. This will be at Z equals 0. It's important to know that's at Z equals 0, and that's ZL. Now at ZL, measurements are always with respect to ground, and if you want to, you can ground that. This is the actual voltage at the load, right here. But it's at Z equals 0. You follow? Here, we're going to have something where we have an input voltage. And typically, you're going to say there's some plus to minus V in here at this point. Don't worry where that comes from. When we're on the transmission line, we're going to have something where we're going to have a forward traveling wave, V plus, and you're going to have a negative traveling wave, V minus. You all follow me on that? Now the equations that dictate both voltage and current on a transmission line using this measurement system would be V, this is from last class, V of Z is equal to V0 plus times e to the minus gamma Z plus V0 minus e to the plus gamma Z. That's for voltage, and for current, it would be I0. But remember, we did the ratio of V to I and call it the characteristic impedance, everyone? So what I can do is simply put I of Z is equal to V0 plus over Z0 plus times e to the minus gamma Z. The next one's important. Remember, the ratio of V to I is the characteristic impedance, and it's always with relationship to the positive traveling wave. But for the negative traveling wave, when we're talking about the current, it's minus that. So it's minus V0 minus over Z naught, and that's Z naught plus, times e to the gamma Z. So these are the two equations that describe voltage and current in the phasor domain on a transmission line. And here, I want to say one thing. When we use these, we almost invariably put the load at Z equals 0. This is an important fact. So we know one thing. We know the voltage at the load is the same thing as the voltage at V equals 0, right? You all agree? And what is that? Get rid of that. Well, that's simply putting Z equals 0 in all these equations, isn't it? If we wanted to get the ratio. And the voltage at the load would be V0 plus V0 minus, right? And if I took that and I divided that by the current at the load, that would be V0 plus over Z naught minus V0 minus versus Z naught. You all see what I'm doing? I'm taking the ratio of V to I, and that has to be the impedance of the load, doesn't it? Can y'all see this? Now, one thing you'll notice is this. Z naught really appears when you multiply top and bottom by Z naught, it really appears in the top. So I can say that ZL right here is equal to Z naught times V0 plus V0 minus, and that's divided by V0 plus minus V0 minus. And now this is the first thing that you have to realize. There's something called a reflection coefficient, and that's the ratio of V0 minus to V0 plus. And I'm going to show you how to get it, but most of you probably see this. If I take this equation, if I put the ratio of V0 plus to V0 minus, I can multiply both sides by V0 plus over V0 minus, and I get V0 plus minus V0 minus times ZL equal to Z naught, right, times V0 plus Z naught times V0 minus. And then I'll collect all the positives to one side. So I'm going to take V0 plus to that side and have V0 plus. And it's times Z naught, right? Minus ZL. And that's equal to V0 minus. And there's a minus sign there. And it would be ZL plus Z naught. And to get rid of that negative sign, I can just exchange those. I can exchange, if I multiply both sides by a -1, it would get rid of this negative sign. And it would simply make this ZL minus Z naught. Follow me? I'm just manipulating this. Then I want the ratio of V0 plus, or V0 minus to V0 plus, so I divide both sides by V0 plus, and then take this over there. And this is the definition for the reflection coefficient. Its symbol is gamma, and there's a sub L to indicate it's at the load. And it's ZL minus Z0 over ZL plus Z0. And this is the reflection coefficient. It's very important. We use that all the time. I'll show you one other thing that's very important. So now what we can do is this. That, we know the reflection coefficient, this is what it's equal to in terms of the load impedance and characteristic impedance, but it's equal to V0 minus over V0 plus. So what's usually done is we rewrite these equations in terms of the reflection coefficient. And now I get V of Z, make sure you write this one down, is equal to V0 plus, and it's going to be e to the minus gamma Z plus the reflection coefficient times e to the plus gamma Z. and I of z is equal to I0 plus, or really, sorry, it's equal to V0 plus over Z0 plus, and it's times e to the minus gamma z minus the reflection coefficient times e to the plus gamma z. So now I have voltage and current anywhere on the line, but I wrote them in terms of the reflection coefficient. Now just take a look at this. The reflection coefficient really is, by definition, well, I'll put it up here. Reflection coefficient is equal to V0 minus over V0 plus. That's what I had down here when I divided this by the side, and I just put it as this. But since that's what it's equal to, minus V0 minus over V0 plus, if I look at that, V0 minus over V0 plus, and I multiply it by V0 plus, I get V0 minus. I'm back to my original equation. Do you follow me? So this is a shorthand way and the most common way to see these equations. Now, this is important you see this. Now, the other thing we'd like is this. We have this transmission line. Just listen. I'd like to know if there's a given length of line, L. I'd like to know what my input impedance would be right there. So it's like I have a length of transmission line, and then I have a load, and I want to know what the input impedance is. That's a reasonable thing to ask. You would love to know that. We want to see how much it fluctuates. And I got to say one other thing about this too. For this to act as a transmission line, remember, L has to be greater than lambda over 10. If it's less than lambda over 10, these wires are basically short circuits, and your impedance is just ZL. You understand? If you just measure across ZL, you get ZL. Well, when these wires are very short, then they don't have the ability to form a wave, to actually get the standing wave patterns necessary for it to behave as a transmission line. But we're going to get the input impedance for that. And to get it, how would you take a guess at how you would get the input impedance? I want to know if I'm going to measure the impedance at this point or monitor the impedance. Would be better. Well, what do you need to get impedance? Just tell me.
Voltage and current.
That's right. And if these are the voltage and current, if I divide one by the other, I have the impedance, don't I? Voltage by current? Sure. So I simply take V of Z by I of Z. And when we do this, I'm going to tell you the V0 plus cancels. I think you can all see that. Right? The V0 plus, it's in both equations. But when I do this, I get Z0 plus here, and then I get e to the minus gamma z plus the reflection coefficient times e to the gamma z over e to the minus gamma z minus the reflection coefficient times e to the plus gamma z. And I want to tell you that's an absolutely accurate equation. That will give that to you. You know what the problem is? I have 1, 2, 3, 4 terms that are exponential I have to calculate. Really, I only have to calculate this once and store it, but I have to use it twice. And I need the reflection coefficient. So what we can do, and I'm just going to tell you this, I don't need to do it now, is if I replace that reflection coefficient with this, right here, and I simplify. This is an exercise in the book. So I would take this right here and stick it where those reflection coefficients are. And then I'd multiply really top and bottom by ZL plus Z naught. And I'd look at, this is what comes out. Now I get the input impedance as a function of Z to be equal to Z naught. Actually, in Whitworth's book, he doesn't put as a function of Z, he puts it as a function of L. And I got to mention something. I want you to just stop writing and look for a second, because this is kind of important. My load is at Z equals 0. This is plus Z, this is minus Z territory. Now when I have a transmission line of length L, it means the position Z here, Z would be equal to minus L. Does everybody see that? This is very important. Not plus L, minus L. So when I put minus L into this equation, you'll notice that this term becomes e to the plus gamma L. You all see that? Because the minus sign would cancel. This would become minus, this would be plus, this would be minus. Now what that does is this. It says that the input impedance, and this is the general one, would be V0 or Z0 plus, and then it would be times times ZL, and then it would be plus Z0 times the TANH of L. And I better put this as a function of L, of beta L, pardon me, of beta, or of gamma L, pardon me, gamma L, not beta, gamma L over Z0 plus ZL times the tan of gamma L. Now this is in his book. This is the formula used for the lossy transmission line. You can just put lossy T line. If you have your books, you can take a look at that. That's Z0 plus ZL plus Z0, hyperbolic tangent of gamma L. And it's divided by Z0 plus ZL. In other words, the actual position of the load and characteristic impedance are interchanged, plus ZL times the tangent of gamma L. Now gamma has alpha plus J beta, right? If you let alpha go to 0, and now this would be for the lossless transmission line, or alpha equals 0, then you would get an input impedance as a function of L, not Z, of L, equal to Z0, and then it would be times ZL plus J Z0 tangent of beta L over Z0 plus J ZL tangent of beta L. And this is the one that's used a lot. This is the most typical one for low loss transmission lines. Okay. That's the input characteristic impedance. I'm going to show you some special cases too. I don't think you had transmission lines in physics, did you? Did you ever have the experiment where they tied a rope to a wall and then they made it oscillate and calculate the velocity and the standing wave ratio, things like that? Do you all remember doing that, something like that in physics? All right, well, about 50% of you do. So when you look at this formula right here, since it's the first time you saw it, you really don't know what to expect. But let me show you some things about this that are important. These are two extremes. If you have ZL as a short circuit equals 0 ohms or a short circuit, it would look like this. Here's the length of the line, L. Here is ZL equals 0. And this is Z equals 0. And I want to know the input impedance Zn, right here. It's 0. We'll take a look at this equation for a second. We do have a characteristic impedance, but we're saying ZL is 0. So anywhere there's a ZL, it would go to 0, right? Now just watch this. If this is 0 and this is 0, what does my equation boil down to? That would be Zn, the function of L, would be equal to Z0, right? And then I have JZ0, tangent, right? Divided by Z0, correct? So really, that Z0 and that Z0 cancels each other. Since ZL is 0, I'm left with JZ0 times the tangent of beta L. Now think about the extremes in value. Beta L represents an angle, right? What happens if I'm at beta L equals 0? Remember, we have a short circuit. What is the value of the input impedance? What's tangent of 0? It's what?
0.
It's 0. So you would expect 0 ohms, and in fact, you get 0 ohms, right? But what happens when beta L is equal to pi over 2? What's the tangent of pi over 2, or 90 degrees? It's infinite. It's approaching infinity, isn't it? Positive infinity. Well, if you come out to beta L equals lambda over 2, so let me just show you this. This equals 0 for beta L equals 0. It's equal to infinity, or approaching infinity, J infinity, to be honest with you, when beta L is equal to pi over 2. That means when L is equal to pi over 2 beta. Now just watch this. That's pi, right, over 2. And what is beta in terms of wavelength? Remember we talked about beta times wavelength equal 2 pi? Right, so wavelength was equal to 2 pi over beta. And so that's 2 pi over beta. I mean, beta was 2 pi over lambda. This is important. So when the transmission line is a quarter of a wavelength long, now please listen. When the transmission line is a quarter of a wavelength long, well, this would just represent a quarter of a wavelength, and we have a short here, the input impedance is infinite. It goes from 0, when it's basically at the load, to infinite when you're a quarter wavelength away. And here's another thing that happens. What would this value be? Just look at this. When ZL is 0, right? When all of a sudden you go half wavelength away, just think about this. Zn here, in general, it's a function of L, is J Z naught times the tangent of beta. Well, beta is 2 pi over the lambda times L. Now just look at this for a second. Suppose lambda is a quarter wavelength. Just look at this. A half wavelength. If it's a half wavelength, I have 1/2 lambda, so the lambdas cancel, right? And the 2's cancel. And I have tangent of pi. What's the tangent of pi, or 180 degrees? 0 again, right? And this is the one thing about input impedance. It's basically periodic in lambda over 2. It starts at 0 if it's a short circuit. It goes to a peak value of infinity, basically going to infinity at quarter wavelength, and then it goes back to 0 again when you're at at lambda over 2. And then it repeats itself. At here it'll be 0, then it'll approach infinity, go to negative infinity, come back to 0 again. And that's the way impedance is actually seen versus length of cable if you short it. Now if it's an open circuit, it's the opposite. We're going to do that next, right here. Now, if ZL is an open circuit, or it's infinite ohms, open circuit, then we have this. That's ZL equals infinity, that's equals 0. Now I've got a length of line L, and I want to know what Zn is as a function of L. And look over here, this is going to be for a lossless case. Velocity line, I've never really had an occasion to use it, to be honest with you. But this we use all the time. So if I look at this right here, what happens when I have an infinite impedance for ZL? Then this term dominates, correct? and this term dominates. Do you all see that? And we can ignore Z naught here. So what that happens is I have Z naught times ZL divided by JZL, where the ZL's cancel, and I have Z naught over J tangent beta L. So I can say it's Z naught over J tangent of beta L, or I can say it's minus J. 1 over J is minus J. Do you agree with me there? And then it would be times Z naught. And then what's 1 over tan? Cotan. I mean, maybe, I know I'm going to have it in not using cotans, but hopefully your calculators still have that function. Cotangents happen. Cotan, it's really just a shorthand way of saying 1 over 10. Cotan of beta L. Now, we can do this. It's really, I almost like this one better because you're familiar with tangent more than you are cotangent. So what happens, what is Z for this one when Z input, when L equals 0? What would you expect it to be?
Infinite.
Infinite, it's an open circuit, right? Is it? Yeah, beta L here is 0, tangent of 0 is 0, 1 over 0 is infinity. Indeed it is. What happens when, and it is, it's infinite. What happens when ZL at L equals lambda over 4, quarter wavelength? Your gut tells you what it's going to be. If it was infinite last time, what do you expect this time? 0, right? Take a look at this. When L is lambda over 4, I have beta, or 2 pi over lambda, times lambda over 4, or I have pi over 2 here, don't I? Tangent of pi over 2 is infinite, 1 over infinity is 0, and indeed I have 0 ohms. And again, this one repeats itself too. Starts at infinity, goes to 0, then goes to infinity again, and that's the way this works. Now, most of the time your load is a 0 or a short, but I'll tell you, when we're measuring electrical distances, if you got wires, squirreling around behind the walls, you can always take the output point and short it, and then we'll show you how to do something called TDM, or measurement. We can do this with time or frequency, and we can figure out the electrical length of that line very easily. You all know what I mean? When they string cable all over the place, you have no earthly idea how long it is electrically, but you can find out. And this is, we always put a little piece, we cap one in with a short, and then we do something called time domain reflectometry, and we can get that. And it's really listening for how long it takes something to echo back after it bounces from one end to the other. All right. Now we did the whole 9 yards. This is the problem that's going to get a little confusing. So you're going to have to watch this carefully. This is important. This is called a full circuit. Wentworth's book's got a great example of this, and I'll tell you about Still Wentworth's book. It is written with the student in mind. It's not written at a high level to just expose you to some pretty complicated mathematical tricks. It's written in a very simplistic way. You could teach this probably to freshmen, a lot of it. It's not a difficult book. So now we do the complete circuit. By that, I mean now I start with a generator, and I'm going to have some plus to minus Vs right here, and I'm going to have some impedance here. I'm just going to call it the source resistance. Then I'm going to have the transmission line, and the transmission line is going to have a length L. Then I'm going to have my load, ZL. And he doesn't do this, but I always ground that point. Ground indicates the zero potential marker in the circuit. Typically, the whole bottom line is that ground potential. And then I measure plus to minus voltage here. And there's going to be a plus to minus voltage here, which would be the input voltage. Now, I'm going to show you how they break this problem apart. Right here, at the beginning of a transmission line, I have an input impedance. You remember how to calculate that? That was that formula with Z0 and ZL and the tangents, right? Now, if I want to figure out the voltage here, here's how I have to do it. First, I do this circuit. I start with my VS, then I put R, the source resistance, and then I replace the transmission line with a simple impedance, just a box here, and I'll call that Zn. Are you with me? So I say the entire impedance is just, the transmission line is represented only by a lumped impedance. And what I want is this voltage here. I want to get plus to minus Vn. With me? Vn right there, how would you get it? Just think about it. What is Vn?
Voltage divided.
That's it. I got two impedances in series and a source voltage, right? That means this voltage, the input voltage, is simply Vs times Zn over Zn plus R source. That's the input voltage. Do you agree with me? That's as easy, and for a circuits problem, that's one of the most basics. Now, if we have that, well, what is Vn? Isn't Vn really the voltage V of Z equal to V0 plus times e to the, let's do this as lossless, by the way. So if it's lossless, it means we don't have a gamma here, we have a minus J beta Z plus reflection coefficient times e to the plus J beta Z, right? But remember the distance L, this is at Z equals 0 here. And this would be at Z equals minus L. So what we can do is say this input voltage here, Vn, which is equal to Vs times ZL, or Zn, pardon me, over Zn plus Rs. That's going to be equal to V0 plus. Now please watch this part. Remember, it's going to be e to the minus J beta Z, but Z is minus L. So this becomes times e to the plus J beta L, pardon me, beta L, plus the reflection coefficient times e to the minus J beta L. And we know the reflection coefficient is given as ZL minus Z naught over ZL plus Z naught. So if we have a given transmission line, as ZL is given, the length of the line is given, operating frequency is given, Vs is given, and Rs is given, we can calculate the reflection coefficient, and we can calculate Vn, and by calculating Vn, we can get V0 plus, can't we? We just simply divide by this on the other side. So if I take Vs times Zn over Zn plus Rs and divide it by 1 over e to the J beta L plus reflection coefficient times e to the minus J beta L, now I have my V0 plus. Yeah, that would be V0 plus. Y'all agree with me there, class? I simply took this and divided it into this. Agree? Now once I have V0 plus, I'm going to ask the class to see who gets it. How do I get the voltage here at the load? Anyone? Well, to get the voltage at the load, what is Z here? It's 0, right? I have this equation, right? I have this equation. And now I have the reflection coefficient. I just calculated V0 plus, right? So if I want the voltage of the load, I just put Z equals 0 here, right? And then I get simply the voltage of the load is equal to V0 plus times 1, right? E to the 0 is 1. 1 plus the reflection coefficient, and voila, I have the voltage at the load. And that's the complete circuit. And that's where we're going to stop. And I went over by 2 minutes, and I apologize, but that thought I wanted to capture. I wanted to finish it. Are you with me, guys? I'm going to give you some more homework for Wednesday, and then please get the book and do the homework this time, and I'll give you the solution, or give you the answers at least, probably the solutions. Any questions about this? you see where I'm going with this? I'm trying to make sure that you understand first the infinite transmission line, then the terminated transmission line. Next time we're doing Smith charts. You know what a Smith chart is? Anyone? You do. Well, I'm going to print some out. They're a handy dandy tool for solving problems very quickly. And they're, if you have if you have equipment to do electrical measurements in microwave, one of the things that pops up on the scope screen always is a Smith chart. They're used all the time. So we're going to go through that. I may go through the entire development, I may not.